Hello, everybody. Welcome to today's lecture. Today we're going to talk about chapter 6.2, which is not a very long chapter, so we'll also be doing 6.3 today, probably. But before we go into that, let's just take a look at just kind of a refresher of what we did in 6.1 through an example. Okay. So, a review of 6.1 real quick. Okay. I'll just draw like a random graph here, okay? So let's say we have this, maybe we have this, and then we have this. Okay, we have this. And then we have this. Okay. So this fits our definition of a graph. We just have a bunch of vertices and edges. So let's give these all names, right? Let's say like A, B, C, D, E, F. Okay. So that's how, so the vertices, we just name them whatever we want. Usually we'll just use letters, capital letters typically. And the edges, we name those based on what the which vertex it starts at and which vertex it ends at. Right. So this edge right here is AB. This one is BC. This one is CD. This one is BD. This one is EF. And this one over here, because it starts and ends at A, it's AA. Okay. So altogether we have 1, 2, 3, 4, 5, 6 vertices and 1, 2, 3, 4, 5, 6 edges. So let's take a look at some of the terminology we looked at last time. Okay, first of all, is this a connected graph? So connected is exactly what it sounds like, right? All the vertices are connected together via an edge. So if you start at any vertex, you're able to get to any other vertex. But here, if we start at A, we can get to B, C, and D by traveling over the edges, but there's no way for us to get to E or F, right? E and F are kind of out here by themselves. So this is not connected. Okay. We could look for any kind of paths in here or any kind of circuits. So there's gonna be lots of different paths, right? Just as a reminder of exactly what our definition of paths was, it is a sequence of vertices where each vertex is adjacent to the next vertex, meaning they're connected via one edge. So like B and C, for example, are adjacent, right? Because they're connected via BC, this edge. So it's a sequence of vertices with each vertex adjacent to the next that starts and ends at different vertices and travels over any edge one time. Okay. So we have to start and end at two different vertices, and we're only allowed to use each edge once. So technically, like AB is a path, right? It doesn't say we have to hit every single vertex or anything like that. These are two vertices that are adjacent to each other. We start at A, we end at B, and we're only using this edge AB one time. A more interesting path would be one that does touch every vertex. So maybe that would be something like AB, AB, CD, right? So we'd start at A, go to B, go to C, go to D. That would be a path. We don't have to go in that order. We could go A, B, D, C, right? We could go start here, go to B, go to D, go to C. There's lots of different paths we can make here. We could just start at a different vertex and like go that way, right? What about a circuit? And actually with paths, we could also have EF, right? We can have EF as a path, but we can't have any other letters in that path because these aren't connected. And we need them to be connected because we need them to be adjacent. Okay, you can't have them be adjacent if it's not connected. So circuit is pretty much the same thing, except we want to start and end at the same vertex, right? So we need it to loop back on itself. So that's going to be a problem if we start from A, right? If we start from A, well, once we go over this edge AB, there's no way to get back to A because we can't use the same edge more than one time. So there's no way we can have a circuit that involves A. The only circuits we can have are going to be in this part right here, right? We could have BCD, for example, BCDB, I should say, where I start at B, go to C, go to D, back to B. So we have to go back to the one we started at. So there's no way we can have one involving A or E or F, right? If we start at E and go to F, there's no way to get back to E without going over that same edge again. So really all of our circuits are going to come from this section with BCD right here. If we want another circuit, we could just go in the opposite direction, B, D, C, B, and then we can start at a different one. We could go C, B, D, C, or the other direction, C, D, B, C. So there's going to be 6 total that we can make. Okay. So that was most of our definitions. Let's remember a couple of other definitions, namely a degree. Okay, so the degree of a vertex is how many edges the vertex has coming out of it, right? So the number of edges at that vertex. So with B, for example, there's AB, BC, and BD. So the degree of B is 3. And that's going to be important when we get to 6.3. I don't think it comes up in 6.2 at all. Maybe it does. For C over here, it's going to be 2, right? Because there's 2 edges coming out of it. For D, it's going to be 2 because there's, again, 2 edges coming out of it. E and F are both going to be 1, of course. And A is going to be 2 because we have AB coming out of it and we have AA coming out of it. Okay. Remember, even though this is loops, it's only 1 edge still. Okay. And also, that's another definition. This one with AA, this is called a loop. That's one that starts and ends, an edge that starts and ends at the same vertex. Okay. All right. So, that was most of the important definitions there. So let's go on to 6.2 now. Okay. So, all right, let's start with 6.2, which is called networks. Okay. So I talked before in 6.1 about how the words graph and networks are usually used pretty interchangeably. They're not exactly the same thing, but they're almost the same thing. So here we talk about exactly what do we mean when we say network. Okay. So a network, so this would be a definition. A network is a connection of vertices through edges. Okay. So let's like think about what this example would mean if we look at this graph up here, right? So a network is a connection of vertices through edges. So that could be like from A to B to C to D. So like our path here would be an example of a network, right? Um, Same with A to B, right? That would be a network. We have this network AB because we are connecting the vertices A and B through this edge, right? So the example the book gives is the internet would actually fit this kind of definition, right? We typically think when we think of the word network, we're typically thinking of internet because um, this is kind of what the internet is. We're not really going into the details of exactly how the internet works, but it's this kind of thing, a connection of vertices through edges in a sense. Okay. And it says like the computers would be the vertices, the connection between the computers are the edges. Okay. So if we were to draw it out, like we could just use this top of the graph here, right? We have computer A, computer B, computer C, computer D, and they're all connected together, right? If we have a network of computers, like at Simmons, for example, with our computer lab and all the computers in the professor's offices and in the administration's offices, right? They're all on the same network. They're all connected together. Okay. And when you connect to the Wi-Fi, you become a part of that network. So that's all we mean there. So we're often interested in this idea, right? Because we're interested in connecting things like this. Maybe not even in the sense of, the internet is one example of that, but we could have other examples like um, if we have like a town or a bunch of towns rather, right? Like if this was um, like if this was New Albany, Indiana, and this is Louisville, right? And this is the bridge that connects the two. The whatever that bridge is called, the 64 bridge. And then this is another city, right? And you have them connected. That would be another example of a network. So it pops up all over the place. So we want to be able to study this kind of thing. So in order to do that, we need to look at some other definitions with things that come into play when we're talking about networks. So the first one is a spanning, what's called a spanning subgraph. Okay, a spanning subgraph. So this is a graph that joins all of the vertices of a more complex graph. But it does not create a circuit. Okay. So it's more like a path, right? It would be a type of path, but it's kind of a special type of path where we're using every single vertex this time. Okay. So for example, up here, we can't have any spanning subgraphs because in our definition, it says that we connect every vertex, but there's no way for us to connect both E and F and the rest of them, right? So there's no spanning subgraphs here. So in math, the word spanning or span typically means it's covering everything, right? And that's exactly what we're doing here. We're covering every vertex. And the word sub in front of the graph, that typically means it's like a if you take your entire graph, it's like a subset of that graph that is also a graph in its own right. Okay. That's typically what we mean by, like, if we have like a set of something and we take a subset of it, it's a smaller set that has the same properties as the larger set. Um, so, like, for example, if we have just for an example of a subgraph, rather, let's just go back up to this one. I don't really need to draw another one. A subgraph would be just this part right here, right? So just EF. This is a graph that is a part of the larger overall graph, right? This whole thing is the graph. This is a smaller part of that graph that's also a graph in its own right. If we just looked at this part, it would still be a graph. This isn't a spanning subgraph because we're not touching every vertex, but it's a graph in its own right. Just like the larger part up at the top here would also be a subgraph, but they're not spanning because they're not touching every vertex. So let's look at an example here. The book has a nice example with towns. So we'll go ahead and just use that one. Okay. I'll try to copy their drawing as best as I can here. And I'm just getting this from page 200 in our book. So we got some kind of weird names here. We have this first one. This is a graph of towns. Okay, these are fictional towns. This one's called Appleville. This one's called Melville. This one's called Clearview. This one's called Heavytown. This one's called Cudstop. And this one's called Snugville. Okay. I'm gonna write that one better. Whoops. Okay. So we have 1, 2, 3, 4, 5, 6 towns, and then we have all these different connections between them. So this is an example of a graph, right? Because it's just a picture of vertices and edges. We have the towns and then the connections between them. So you could think of these like roads, or maybe there's water in the middle here. So some of them are bridges, some of them are roads. Whatever the connections are, it's all basically the same idea, that we just have some towns and then these are the ways in which they're connected. So first of all, let's think about, why would we care about a spanning subgraph? So a spanning subgraph would be a smaller version of this that connects all of the vertices. Well, maybe we want to have an efficient route where we go through all of these, right? Like maybe we're delivering packages or something, and these are the only ways to get between the different cities. And we want it to be efficient, so we don't want to go over the same edge more than once. We don't want to go to the same vertex more than once. And maybe, we don't want it to be a circuit. So in this instance, like maybe we like start in one place and then we have to drop the truck off at a different place at the end or something like that. Okay. So what would the spanning subgraph be, or a spanning subgraph? There's not necessarily only one. Well, let's look at this. Okay, let's use this so we can see it here. Let's say we're starting at Cudstop. the only real thing we need to worry about is that we touch every single vertex, okay? So all we really need to do is go along the outside here, all right? Because now we're hitting every single one of them, right? So this would be our path here. So we start at Cudstop, we go up to Snugville, then we go to Appleville, then to Melville, then to Clearview, then to Heavytown. All right, and that's not the only way we can go, but this is a graph. So just the black line here it's a graph in its own right. The pink one is the big graph, but the black one is also a graph because it's just a collection of vertices and edges. And we're touching every single vertex, right? So this would be a spanning subgraph. There's other ways we could have went. We could have gone Cudstop, Snugville, Appleville, Melville, down to Heavytown, then up to Clearview. That would still be a spanning subgraph. So notice we say A, and it's not the spanning subgraph, right? So there's going to be more than one of them. Our only real criteria is that we hit every town or vertex or whatever it is one time, right? Now, I also mentioned, like, we want the path to be efficient, so we don't want to use the edge more than one time, but that's not even in this definition, right? It'll be part of a later definition. But here, it doesn't even necessarily say that we can only use every path one time, every edge one time. So let's go ahead and let's use green here. So if we started at, say, Heavytown, right? This is figure 6.2.3 in the book. We could go to Melville, and then we could go back, and we could go to Clearview, right? And then we could go to Appleville, and then we're like going back, and then we're going to Cudstop, and then Snugville. Okay, so we're hitting every point here. So it doesn't necessarily have to be a path. I feel like I misspoke earlier and said that this was a path. I might have. If I did, I apologize for that. It doesn't have to be a path. A path would be a path where you connect every vertex would be a spanning subgraph. But a spanning subgraph isn't necessarily a path. So not the same thing. You can have paths that aren't spanning subgraphs, and you can have spanning subgraphs that aren't paths. But if you have like a path that connects every vertex, then it's automatically going to fit this definition too. But the other direction isn't necessarily true, right? If you have a spanning subgraph like we do here, it's not a path, right? Because a path, you can't use the same edge more than one time. Okay. So let's, we'll come back to that in a second. So let's talk about another kind of related thing. Well, related to this example at least, not necessarily to the spanning subgraph thing. So this is a tree. Okay. So what do we mean by a tree? A tree is a graph that is connected and has no circuits. Okay. And I mean, that's it. Okay. So why are we talking about this right after the spanning subgraph? Well, a spanning subgraph is a graph that connects all of the vertices and does not create a circuit. This is a graph that is connected and has no circuits, right? If a spanning subgraph is connecting every single vertex, then it has to be connected, right? If it's disconnected, it can't touch every vertex. Sorry. So a spanning subgraph automatically would be a tree. Okay. So spanning subgraph is a tree. The other way, though, a tree is a tree always. Oops, I forgot to write subgraph. Sorry. So a spanning subgraph is a tree. Is the other direction true? Okay, is a tree always a spanning subgraph? Well, if we have a tree, then it's a graph that's connected with no circuits. So we have the no circuits part. We do need it to be connected, but notice that a tree doesn't necessarily have to touch every vertex, right? It just has to be connected. So it doesn't a tree doesn't necessarily have to be a spanning subgraph. So the other direction is not necessarily true. It is not always a spanning subgraph. Okay. So sometimes it will be, but it doesn't have to be. So let's talk about some properties of trees. Okay. It gets its name because that's kind of what it looks like. If we think about this graph right here, the green one that we drew right here, okay, the green part, it's a graph, it's connected, and it has no circuit. So this would be a tree. The black one would also be a tree, right? You can't really see it anymore because I covered it with the green one. But we went from here, 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 here to here. So that would also be a tree. What about the pink one, the overall thing? Well, that one would not be a tree because there are circuits in it, right? We could go Heavytown, Cut Stop, Melville, back to Heavytown. So there's ways to get back to where you started without having to go over the same edge more than once. So there are circuits there. So therefore, it is not a tree. The pink graph, the overall graph, is not a tree. Okay. It's also not a spanning subgraph because same thing. It has circuits in it. So let's look at some properties of trees. Okay, so properties of trees. So number one, if a graph is a tree, there is one and only one path joining any two vertices. Okay. If a graph is a tree, then there is one and only one path joining any two vertices. So in other words, whoops, sorry, I keep hitting this. Going back up to this first one here, we can tell automatically that this top part of the graph Ignore E and F because we need it to be connected anyway. So with E and F, it's automatically not a tree. But just looking at the top part even, this can't be a tree because we already have there's two different ways we can get from A to C, for example, right? We could go A, B, D, C, like we did in the last one right here. But we could also go A, B, hang on a sec. I think I chose the wrong one. Yeah. Sorry, we want to go the other direction from C to A. That's how there's two different ways. If we start at C, we could go C, D, B, A, right? C, D, B, A. That's one path to get from C to A. But we could also go, yeah, we could go C, B, A. Right, we could just skip this one. And so there's two different ways to get from C to A. So this would not be a tree. And actually, starting at A would work too, right? We could do A, B, D, C, but we could also just do A, B, C. Sorry, I was thinking we needed to use D for some reason, but we don't. So these are two different paths to get from A to C. We could either just go straight forward, A, B, C, or we can go the long way and go from A, B, D, C. So we automatically know that this can't be a tree because if it was a tree, then there would only be one path joining any two vertices, right? So what about if we flip the statement around? Is it true that if there is one and only one path joining any two vertices, it's automatically a tree, right? We know the converse of statements aren't always true, right? Here we have a spanning subgraph as a tree, but it's not necessarily true that a tree is always a spanning subgraph. Is the converse here true? And the answer would be yes. If there's only one path joining any two vertices, then we can conclude that it must be a tree. Okay. So the converse is true too. So i.e. if there is one and only one path joining any two vertices, then the graph is a tree. Okay. So another way to state this, like logically speaking, is that a graph being a tree and there being only one way to get from one vertex to the next are equivalent statements, right? You can kind of switch between them. If you know one, you automatically have the other. So if we're looking to see is something a tree, then all we need to do is say, okay, is there only one way to get from one vertex to the next? So let's look at the green one right here, right? The green one's the easiest one to see because it's on top. If we start at Heavytown, there's only one way to get to Clearview, one way to get to Melville, one way to get to Appleville, one way to get to Cudstop, one way to get to Snugville. Okay. And the same would be true for any of these, right? If we start at Snugville, we could go to Cudstop, and then we could go this way to Heavytown. To get to Melville, we'd have to go here, then here. So there's only one way we can go for all of these. Trying to make sure that I can't find a counterexample here. I don't see one. So we can safely say that this green is going to be a tree. Okay. On the flip side, if we just were told it's a tree, then we would automatically know, okay, there's only one way to get from Heavytown to Snugville. There's no reason to try to find another way. Okay. So this is the biggest property. This is like the number one property of a tree. Okay. We have a couple of other trees though. A couple of other properties. So let's look at those. And this section is actually going a little bit longer than I anticipated. We still have quite a bit to do here, so we probably won't do 6.3 today. So in a tree, every edge is a bridge. So let's remember what a bridge is, because that was like the one definition I didn't review at the very beginning. Okay. So a bridge is an edge where if you take it out, the graph is no longer connected. Let's go back up. Yeah, this would be a good example if we just ignore E and F. Okay. So just forget about E and F for now. And let's just look at the graph A, B, C, and D. Okay, so just this top part right here. If we include E and F, it's already not connected, so it wouldn't matter. But if we just look at the A, B, C, D part, and look at this as a graph, notice if you take out AB, well, first of all, if we just look at the A, B, C, D part, it's connected, right? There's an edge connecting all of the vertices. But if we take out AB, now it's no longer connected, right? So AB is a bridge because it's the only link between A and B. BC is not a bridge because if we take BC out, okay, we can still get from B to C. We just have to go to D first, right? We go BD, then CD. Same with CD, same with BD, because we have these alternate paths. For A and B, there's only one way to get from A to B and vice versa. So if we take that one out, the graph's not connected anymore. So AB is a bridge. So with that in mind, let's go back down. In a tree, every edge is a bridge. So if you take any of the edges out, it's not connected. So let's look at our tree right here with green. So we can confirm Heavytown to Melville. That would be a bridge because it's the only way to get from Heavytown to Melville. Heavytown to Cudstop, that would be a bridge. It's the only way to get between these two. There's no alternate paths here. So a bridge is basically if there's no alternate way, then it's a bridge, right? It's the only way to get there. To get if we have this one from Heavytown to Appleville and we take that out, then it's no longer connected, right? Because Appleville is not connected to Heavytown in any way. Just looking at the green part. Okay. So like in this kind of sense, like if we think about a real life bridge, like the 64 bridge between Louisville and New Albany, like I was talking about before, for example, it's not really a bridge in the same sense because if you take away that bridge, you can still get from New Albany to Louisville, right? You just have to go to Clarksville, then go over the 2nd Street Bridge, and now you're in Louisville. You have this alternate path. So it's not a bridge in the same way. So it's more like if New Albany was like this isolated place, right? And there was no Clarksville next to it. Or it was just this one city. And then on the other side of the bridge, you had Louisville, and it was just that one city. If that was the only bridge going over them, then that's what we would mean here by a bridge. Okay. All right. Let's talk about the converse. Is the other way true? If every edge is a bridge, do you automatically have a tree? Well, if every edge is a bridge, let's go back to our definition of tree. Okay, it's going to be a graph. We don't have to check that. if everything is a bridge, there's no way you can have a circuit because that means that there's no alternate paths, right? If everything is a bridge, that means there's only one way to get here. So there would be no way to get, like, if you could go from Heavytown to Melville, for example, there's no way to get back to Heavytown without going over that same edge. So there's definitely not going to be any circuits. So now we just have to worry about, is it connected? Well, if everything is a bridge, by definition, a bridge is connecting two vertices. So yeah, it's going to be connected. So the converse would also be true here. Conversely, if every edge is a bridge, the graph is a tree. So again, in other words, these are equivalent statements. Having a tree and every edge being a bridge are the same thing. If you have one, you have the other. Okay. Two more properties of trees. Let's use light blue. A tree with n vertices. Okay, n is a number here that we don't know what it is. So a tree with n vertices, meaning whatever number of vertices. So for example, the green part right here, which is a tree, has 1, 2, 3, 4, 5, 6 vertices. So here n is equal to 6. Okay. A tree with n vertices must have n minus 1 edges. Okay. So if, like in that example, we had 6 vertices, that means we must have 5 edges. Let's go count them and make sure it's true. So if we have 6 vertices, we better have 5 edges. We have this one, this one, this one, this one, and this one. Okay. So it is true here. 1, 2, 3, 4, 5. Remember, this isn't one long edge. You divide the edges between the two vertices. So the edge between Heavytown and Cudstop is an edge, and between Cudstop and Snugville is also an edge. Okay. So our definition checks out here. All right, so what about the other direction? If we have n vertices and n minus 1 edges, does that automatically make it a tree? Well, probably not. Let's see if we can come up with a counterexample. Do we already have a counterexample? I don't know that we do have a counterexample drawn. It might be hard to come up with one. Let's think about it. So let's say we have well, I guess the best example, we could just draw a not connected graph, right? Well, that doesn't work. Yeah, it might be hard to come up with a counterexample. I'll try to post one after what I have more time to think about it. Or it would be a good, or feel free to try to come up with your own counterexample. Can you, for example, take something with 5 vertices and 4 edges that's not a tree? Okay. I'm not even positive you can. I'm just trying to think of it kind of on the fly here. A connected graph. So property number 4 now, we'll move on and think about that one. Kind of keep it in the back of your minds to think about afterwards. So a connected graph with n vertices, whoops, n vertices and n minus 1 edges must be a tree. Okay. So here's our partial answer. If the graph is, so this is kind of like a partial converse, right? If we have n vertices and n minus 1 edges and it's connected, now it must be a tree. So I was trying to draw a counterexample without it being connected, but it was still pretty hard. But if it is connected, then automatically it must be a tree. So if we just think about, if we have 5 vertices and 4 edges, right, here we have 3 edges. If we have this one as our 4th, now it's got to be a tree. If we make this one the 4th, it's got to be a tree. Any combinations of 4 edges and 5 vertices would have to be a tree, or 3 edges and 4 vertices, or 100 edges and 101 vertices, right? Then it would have to be a tree if it's connected. If it's not connected, it doesn't have to be a tree. Here, I thought of a counterexample right now, actually. I wasn't thinking about a loop. There you go. So a loop's kind of an easy way out of this. If we draw it like this, now we have 5 vertices and 4 edges, but this is not a tree because it's not connected. If it's not connected, it automatically can't be a tree. Okay. So this would be a good counterexample right here. Trying to erase it. There we go. Yeah, but still see if you can come up with your own. Maybe try doing one without a loop. Is it even possible without a loop? Okay. I can think of another way to do it without a loop. So maybe try coming up with one without a loop. Okay. All right. So, the textbook goes through some more examples with this, which we kind of just did like on the fly as we talked about each one. But feel free to read through that. And then it also gives some more examples of trees. Actually, one kind of like fun example of trees, which you might notice if you look at Canvas. Okay, actually, let me pull up Canvas for you guys. So look at our class picture here. All right. This is a scene from Good Will Hunting, the movie. And if you're watching this in like a future semester, not fall 2020, this was the picture that was up here. Okay. Make sure I don't have any information on the sides here. I do not. If you look in the picture of Good Will Hunting, that's exactly what he's drawing right here, right? These are trees. And the problem that he's like solving on the chalkboard, if you've ever seen the movie, there's like a problem on the chalkboard, and it's supposed to be like a really hard problem. It has something to do with drawing all the different types of trees. I don't remember exactly what the problem is. Maybe with all the same number of vertices and edges. I'm not exactly sure. But that's the problem that he's doing right here. These are all examples of trees. Okay. And it's not exactly a difficult problem either. We could probably do it with just a little bit more like definitions and a little bit more work. But if you've ever seen that movie, yeah, that's what he's doing here. All right, so let's talk about the like why we want to know about this. Okay, what's the point of talking about these trees here? Well, the idea that we're working up to is this: the minimum spanning, so let's just say a minimum spanning tree. Okay, so a minimum spanning tree is the tree that spans, whoops, all of the vertices in a problem with the least cost. Okay. So what do you mean by cost here? The book gives two examples. It could be time, could be distance, could be like literally cost, like money. So remember spanning, like I said, it means it covers everything, right? The minimum means we want to keep it as small as possible. What we want to keep as small as possible depends on the context. Now, let me underline this. So first of all, this has to be a tree. So it has to, follow our definition of a tree, which was a graph that is connected with no circuits. It has to touch every vertex. Okay. So this is similar to the spanning subgraph because now it has to touch every vertex. And we want it to have the least cost. Okay. So there might be more than one way to go to have a tree that touches every vertex, but we want the one that has the least cost. So maybe it's the least amount of distance traveled, or the one that takes the least amount of time. Okay. And there still could be a tie, but in general, the examples we'll look at, there won't be a tie, there will just be one. But the idea here is now, how would we even go about finding this? Because in a lot of problems, there's going to be many different ways that we could come up with trees that touch every vertex. Just going back up to this one right here, we found one way, right? We have this one tree with the green, but the black one, that would be a tree too. It's a graph, it's connected, and it has no circuits. Which one of these is better? We might think the black one because we're not covering that much distance, but maybe there's an even shorter one. How do we know? Okay. So let's talk about that. Well, let's look at this example first, where I'll just kind of like show you the answer. And then we'll talk about how do we come up with the answer. Okay, so this is just the example from the book here. All right, so let's say we have this graph. Okay, so we have all these vertices. And we'll call it A, B, C, D, E. And now we're actually going to put distances between them. Okay. Now, I mean, the book isn't specifying that these are distances because it's not really drawn to scale, right? Like it looks like this one and this one should be equal, for example. But we're going to use slightly different numbers. So we're using the word more generally cost because we could think of that as like a distance or a time or a bunch of other different things. Um, like you could think of it literally as a cost, like maybe tolls. Like maybe the toll to cross from A to E is $10, and the toll to go from B to D is $11 or something like that. Or you could think, okay, there's 10 miles between A and E, or it takes 10 minutes to get from A to E. It takes 11 minutes to get from B to D. There's a lot of different contexts we can put this in. So we're using the word cost very generally here, not necessarily just as money, but as anything. So we'll say this is has a cost of 24. This has a cost of 28. This one is 9. This one's 8. And then we're also going to have these in the middle here. This is going to be 30. Maybe I should write this kind of up here. This is 30. And this is 25. Okay, so to go from B to E, it's 30. To go from A to D, it's 25. Let's just think of it as time, right? Let's say it's in minutes. Like it takes 10 minutes to get from A to E. It takes 30 minutes to get from B to E. So even though it looks like A, B, and ED are the same distance, maybe we could think of like there's more traffic on ED, right? Or there's more barriers. Like you kind of have to go a little bit more of a roundabout way. So we'll think of it in minutes. So what do we want to know? We want to know what is. Sorry, let me get the question here. What's the minimum spanning tree here? Meaning, what's the quickest way we can hit all of these with the least amount of cost, which in our case is going to be minutes. So in our context here, what's the fastest way we can hit every vertex? So it doesn't matter which one we start at or we end at. We just want to know, okay, let's say we're planning our route. What's the fastest way we can hit every single one of these? Okay. And the book just kind of gives you the answer for this one because we haven't talked about how do we find that. So the minimum spanning tree for this one is going to be E to A to B, B to C, C to D. Okay. So E, A, B, C, D is our the path that we're taking. It's the tree. We're hitting every vertex, so that's important. The cost, which we're saying is time, is 10 plus 24. So the 10 is going from E to A, the 24 is going from A to B, plus 9 going from B to C, plus 8 minutes to get from C to D, for a total of 51, right? And that's in minutes. So it would take 51 minutes. So if you don't believe this is the fastest route, that would be a good exercise to try, right? See if you can find a faster route, which there shouldn't be one here, but it's good just to try, just to kind of see what the idea is, right? Like for example, why is we could go like one that might jump out to you. What if we go just directly from E to B? Why do we have to go this roundabout way? But remember, we also need to hit every single vertex, right? So that would be why. Well, what if we go from E to B, back to A, over to D, and then to C? Well, it's eating up a lot of time to go from E to B and from A to D. So just that alone is already more than 51. So it's a good idea to try some different routes though and see if you can come up with um you're not going to come up with one that's shorter. Maybe you could try to find the longest path. Maybe you could find one that's close to being shorter. Um just play around with it a little bit. All right, so we have one more thing to talk about in this chapter, this section, okay, which is how do we come up with this, okay? So there's an algorithm for it. An algorithm is like a method, right? It's like a method that you can always do. You can always follow these steps in order to achieve your goal, right? So we use it in math sometimes, but if you ever take computer science, you'd probably talk about algorithms a lot because that's how you achieve things with computers. If you want the computer to achieve a certain goal, you say, okay, try this, then try this, then try this, etc. Right. Um, you already know some algorithms that you might not know that you know, right? Like the addition algorithm, right? If we want to do 103 plus 81, the algorithm is add the ones place, then add the tens place, then add the hundreds place. Okay. So this would be an algorithm. You just probably never called it that. So let's look at the algorithm or the steps for how we um, come up with the minimum spanning tree. And this is not just any algorithm. This is what's known as Kruskal's algorithm. So it's named after this guy, Kruskal or Kruskal, maybe. It's probably Kruskal. I don't know. I don't know what language it is, so I don't know how to pronounce this. So this is like steps you can take no matter how complicated the graph is so that you can always come up with the minimum spanning tree. Okay. So let me just write here for finding minimum spanning um, sorry, spanning tree. All right. So step one, we want to find the cheapest edge. Okay. So cheapest because we're thinking of it generally in terms of cost here again, right? So that would be if we're thinking about this in minutes, which one is the shortest amount of time to get from one to the next? Or which basically you just look at this and you say, okay, what's the smallest number? Okay. So, but the book words it as find the cheapest link. Whoops. Um, it's using the word link here. Um, but that just means edge. Okay. Sorry, I know I write my K's weird too. I'll try to not do that. Okay. So find the cheapest link. So going back to this graph up here, what's the cheapest link? Well, that would be DC, right? This one's only 8. It's the smallest number out of any of them. So that's what we would do first. We find the cheapest link. If there's more than one of them, just pick any one of them. It doesn't matter which one. If there's a tie, just pick one. Okay. And then you want to mark it. So you don't want to lose it. So mark it in whatever way you can. Here, let's look at another example just so we can kind of do the algorithm as we go. Okay. Um, so this is similar to the last one, but I'll add some more on here. Okay, so we have I'll just add another side to it, and I'll change the numbers this time. Okay, so we have these, but now we're gonna have different numbers. I'm just gonna make these up at random. 30, 31, 12, 14, 7, 6, 5, 4, and then in the middle here, right, these are going to be 40 and 44. Okay. So here's another graph. We want to find the minimum spanning tree. So step one, we need to find the cheapest link. So what's the smallest number in this graph? Well, that's going to be between F and E, right? 4. So I'll mark this. So this is where we're going to start. Okay. So what's step 2? Step 2, well, find the next cheapest one. Okay, easy enough. Find the next cheapest link. And of course, you're going to want to mark it. So I'm not even going to write that down. So what's the next cheapest link? Okay, that's going to be F to A, right next to it. It doesn't have to be right next to it, but in our case, it just ends up being the one right next to it. Okay. All right, now what do we do? All right, step 3 is just continue doing this as long as you do not make a circuit. Okay, we're really trying to avoid making a circuit here. So just keep doing this and making sure that you don't make a circuit. As long as you do not make a circuit. So let me write down the 4th step before we continue so we know where to stop. Okay. So you are done when the tree, I'm just paraphrasing what the book says, hits every vertex. And remember, with a tree, you can't have a circuit. Okay. So let's keep doing that with this graph. So now we want to hit the next cheapest one. Well, that's going to be over at B and C, right? That's 6. That one costs 6. Now next is going to be C to D, right? Because this one costs 7. The next cheapest, well, the next cheapest is A and E, but if we do that, we have a circuit, right? Because we are going back to E. We would have E, F, F, A, back to E. And we don't want to go back to any of them that we already hit. So we're going to ignore AE, even though it's the cheapest, because we don't want to make a circuit. Okay. So the next cheapest would be BD, 14. Again, we would make a circuit here with BCDB, right? If we fill this part in, we could go from B, C, D back to B. So we'd have a circuit. We'd have ones that like loop back around to the starting one, and we don't want that. So then we go to the next cheapest. The next cheapest is going to be AB, which is 30. Okay. And then the next cheapest, well, actually, we're done now, right? We don't even need to do anymore because we've hit every vertex. We hit E, F, A, B, C, D. Okay. So once we hit everything, we're done. So this is the minimum spanning tree. If we want to know the overall cost of it, we just add it all together. We do 5 plus 4 plus 6 plus 7 plus 30. Okay, so we have 9, 15, 22, 52, I think. All right, 9, 15, 22, 52. Yep. So the cost here is 52. All right, so I think that's everything in this chapter. The book has a few more examples that are different from mine since I just like made them up. So definitely look through the book's examples. But in general, this isn't such a bad one to follow, right? We just find the cheapest one and then we go to the next cheapest one. And we say cheapest, we just mean the smallest number, right? The graph will already be given to you. The numbers will already be there. So you just look for the smallest one, then look for the next smallest one, then just keep looking for the next smallest one. And the only thing you have to make sure you're not doing is you're not making any circuits. And then you just keep doing that until you've touched every vertex. Okay. So definitely look through some of the book's examples. And I'll do one more example before we go here. I know this video is going pretty long already. But this is the only one that's for this class. And there's going to be some homework problems this week that will involve this as well. So you'll get some practice. So I'll just make one at random here. I don't want to use the same one as the book so that you have some more examples to look at. Okay. This is kind of similar to the city one we did earlier, I guess. I just kind of inadvertently made it that way. It's not exactly the same. We have less vertices, and that one didn't have any numbers, so it's not quite the same thing. Let's say A, B, C, D, E. And so we're going to give numbers to these. Let's say, and you can think of these as distances. Let's do that. Let's think of it as distances this time. So this is distances in miles. So let's say there's 4 miles between A and B. There are 10 miles between B and C. There are 15 miles between C and D. There are 20 miles between C and E. Between A and E, there are 9 miles. Between E and D, there are 7 miles. Between B and E, there are also 7 miles. Let me write it on the other side so we don't get confused with BD. Between A and D, let's see, we'll say about 21 miles. And between B and D, it is, I'm trying to make it make sense. Let's say 8 miles. I think that's all the combinations. All right, so we want to find the minimum distance. So what's the shortest distance? What's the path with the shortest distance that will allow us to hit everything? That's what we're looking for here. We want to hit all of these places, A, B, C, D, and E, and we want to do it with the shortest distance traveled. We can start in whichever one we want. We can end in whichever one we want. So we start using the algorithm. First, we find the shortest one, right? The shortest one here is going to be AB, okay? AB. Because that one's only 4. Now we go to the next shortest one. Well, we actually have a tie, right? B and E is 7, E and D is 7. And what our algorithm says is to pick either one. So let's just pick B and E because that one's it's connected to this one already. So we'll just pick these two. Now if we go to the next shortest one, well, that's going to be the other one, ED, right? Because that one's 7. And this whole time we want to make sure we're not creating any circuits. So the next shortest one would be 8 to go from B to D, but that one, that's a circuit, so we don't need to do that. So we'll instead go up here to 10 with BC, right here, because that's the next shortest one. And now we're done. Now we've hit everything, right? We've hit A, B, C, E, and D. Okay, so this is the minimum spanning tree. The distance or the cost, and we're just pretending that it's distance, is going to be 4 plus 7 plus 7 plus 10, which is going to be 28. Okay. So this one would be a good one to maybe try on your own. Maybe what happens if you pick the other edge first, if you pick ED first. Okay. I mean, it's gonna be basically the same thing, but you could try doing it that way. See if you can come up with a distance that you think might be shorter in this one, right? Make sure the algorithm works. Maybe change the numbers around and try it your own way. Like I said, there will be more in the homework for you to practice on, and there's different examples in the book if you want to practice there. Okay. All right, so that's definitely all the time we have for today. This one went a little longer than I expected, so we're not going to do 6-3 today like I was expecting to, but we'll probably look at both 6-3 and 6-4 next time. I'll split them into different videos, but they'll probably be on the same day. So I'll see you guys for that one. Let me know if you have any questions. And thanks for watching.